Welcome. Today we will be taking a look at the notes worksheet entitled Rational Functions Day 2. We'll elaborate and expand on some of the graphical and algebraic characteristics that we looked at on the previous notes worksheet, and I will do some examples obviously to solidify some of these skills. So let's start with example 1. It is a completely oversimplified economic problem, but I like it nonetheless because it does relate to one of the things we talked about on the previous worksheet. So let's give it a try. Two companies here, and it says the total cost C for company A to manufacture n units of a product is conveniently given by this linear function right here. Okay, not a big deal. So $400,000 really plus 500 times the number of units that they manufacture. All right, not a big deal. Then the total cost for company B to manufacture n units of the same product is, and then again, just a convenient linear function here, and this would be $1 million plus $450 times each unit that they manufacture. All right, so total cost for each company. What I would love for us to do then is, for letter A, write an average cost. So when we talk about the average cost, another way to phrase that would be the cost for each product that is manufactured, cost per product. And so basically what we're going to do in terms of average is what we've kind of been doing all along with average. We're going to add up the total and divide by however many we have. So in this case, again, just very conveniently and just to expedite this along, we have the total, right? So for company A, the total cost is this right up here. So that's going to be the total. That's adding up the entire cost. And then obviously here's our per, so kind of the division symbol, and divide by however many we have. And in this particular case, how am I going to represent that? What do you think the denominator will be? So this would be the total divided by the number that they manufacture, and that was already given to us, of course. That's your n. All right, very nice. Now I come over to the second company there, company B. Let's get an average cost for them. Again, total divided by however many that they manufacture. So $1 million is the fixed cost, $450 is the variable cost as we multiply that by the number of units. And in this case, to get the cost per product, we'll divide by n. All right, so the total cost, and then divide that by however many they manufacture, and we've got that. Perfect. Now let's jump to part B. It says, what happens to the average cost for each company as n gets large? So basically, as n is going to approach infinity, as the number of units manufactured increases dramatically as it gets larger and larger and larger. And basically what this means, and I'm going to just write it off to the side, as the input gets larger and larger and larger, that's another way for us to just discuss end behavior. All right, so I need you to think back to the previous day's lesson and think, how did we talk about end behavior? Well, if you remember, we referred to it through what we called the horizontal asymptote. As n gets larger and larger and larger, the function values approach a particular number. And as they approach that particular number, a horizontal asymptote is produced on the coordinate plane. So, now let's think back. What if I asked you what the horizontal asymptote is of this function right here? Remember how it plays out, everyone? We compared the degree of the numerator to the degree of the denominator. And I hope you all see in terms of this would be n to the first over n to the first. They're the same. When the degrees are the same, then we just look at the leading coefficients. In this case on top, the leading coefficient would be 500. On the bottom, it would be 1. And so what we can pretty much say is that as n gets larger and larger and larger, the average cost is going to get closer and closer to $500. Okay, then we come over here and we repeat that process, of course. Same deal, degrees are the same, n over n, ratio of the leading coefficients, guys, so 450 over 1. And so if we were to track this out, and again, I won't graph this and put my table in place, but if I did, and track this as n gets larger and larger and larger, what we would see is that the average cost would get closer and closer to $450. So you can kind of see the ideal here. And for part C, if we can draw just a quick conclusion and move on, it just says which company is in a better position to offer a competitive price if there is a large demand for the product. And in this case, if you look at their costs, well, Company A had to put up $1 million up front compared to this is Company B, compared to this company here that only had to put up $400,000, but the variable costs here are lower than here. And what happens in the end is that obviously this gets lower and lower and lower than this would. And so if there is a large demand and they had to manufacture more and more of these, the cost per product is lower for Company B. There you go. All right. Again, completely oversimplified, but again, it does relate nicely here to one of the characteristics we explored yesterday. Great. Let's move on. So what are called oblique asymptotes. The third type of asymptote, we saw vertical, we saw horizontal, and this one essentially will be a diagonal. I'm just going to write that above there. We're going to call it oblique, but for lack of a better description, it is a diagonal asymptote. And it occurs in one very particular situation. Just so happens they're the particular situations that you see right here for functions f and g. And it occurs when the degree of the numerator is 1 greater than the degree of the denominator. And let's see if I can get this in. Degree of the denominator. This is another way to describe end behavior, by the way. So we'll be looking at the ends of the graphs, of course, and take a look at it in relation to horizontal. So if I asked you to look at this particular function right here, you would tell me that there is no horizontal asymptote from yesterday. Degree on the numerator is greater than the degree on the denominator. If it is 1 greater, as it is here, x to the second over x to the first, it has a particular end behavior that can be described approaching what is called an oblique asymptote. And so we'll see that here. No horizontal, but an oblique. Same deal here. If I asked you for a horizontal asymptote, you would definitely tell me none. But in this case, 1 bigger on top than on bottom, it has what's called an oblique. So let's go ahead and just see this in action. And let's see what it says. So letter A. It says divide the numerator of each function by the denominator and ignore the remainder. So in this case, we're going to do a little long division, kind of a review from the beginning of the semester. And we're going to go ahead and ignore the remainder, though. So here's the idea. Divisor, dividend. And watch what type of quotient I get here, and kind of hence what happens graphically. So, I can run through this process a little bit. It's been a little while, but I'm sure we can pick it up pretty quickly. So first and foremost, I would ask myself, how many times does x go into x squared? And, it should be x there, of course. And then we bring that down, and I say x times x is x squared. That looks great. Subtraction out in front. And so when I subtract, these are going to cancel, and I bring these down. 2x minus 0 is 2x. 1 minus 0 is 1. That looks great. And then, of course, I repeat. How many times does x go into 2x? It goes in 2 times. And then I multiply back on down. Again, you can rewind this if you don't remember, get a little review. But basically, multiply the 2 into the divisor, back on down, and I get 2x. Subtraction. These are going to cancel, and I get this right here. And in essence, this is our remainder. So I'm just going to write remainder, but with these obliques, it doesn't really affect what we're looking at. Now, if you look at this in particular, we've got this quotient right up here, which is x plus 2. And I had basically said that the quotient is going to be our oblique or diagonal asymptote on the coordinate plane. Well, it is a line on the coordinate plane. And think about this. How is a line modeled on the coordinate plane? With what equation? Well, of course, we know that lines are modeled with y equals mx plus b. And if you look at this carefully, of course, doesn't this fit that mold right there? Mx plus b. And so as a result, it says right down here, what is the oblique asymptote for each function? Well, for right now, guys, I'm going to say that it's y equals 1x plus 2. And now I want to see it. So let's go for it. Let's just check this out, just see what it looks like graphically. When we divide, and if you would like to look at this in a little more further detail and kind of get the ins and outs of it taken care of, please call me over and we can look at it. But basically, this is going to be our way to find this diagonal, our oblique asymptote on the coordinate plane. So everyone, I grab the calculator, I do this, divide by x, that's looking great. I'm going to zoom standard, and notice, of course, there's no horizontal asymptote, right? So as I go to the left of my graph, this is really just shooting down. As I go to the right on my graph, this is really just shooting up. But rather than just kind of talking about it in very general terms, we can be a little more specific with those function values. They seem to be approaching, and if you can kind of see, there's a boundary there, isn't there? Even though I haven't put it in just yet, it seems like there's a boundary off to the right and left, and I'm hoping you see that when I go ahead and go back to that y equals and type in x plus 2, look at that. Does that line kind of fit as a boundary for the end behavior on those graphs? Yeah, no question about it. And so ultimately what happens is the function values up here, as x gets larger and larger and larger, get closer and closer to the function values on the line y equals x plus 2. And you can see that right there. It's a diagonal boundary to the graph. We obviously had a vertical boundary, right? There's your x equals 0. Remember, of course, vertical asymptote, x equals 0. There it is. And now we've got, for our hyperbola here, a diagonal boundary. That's pretty cool. Hey, let's do one more, and then we'll go ahead and hit the next piece. So divisor is the denominator. Dividend is the numerator. Now, this doesn't look pleasant, but let's see if we can pull it off. So again, good review on some long division there. And remember, focus on the leading term in the divisor, the leading term in the dividend. So how many times does x squared go into x cubed? Well, it goes in exactly x times. And then I multiply this times the entire divisor. So there's my x cubed, which what I expected. X times x is x squared, and x times negative 6 is negative 6x. Great. These cancel. Let's subtract going on down. I'm getting a negative 5x squared on that end, and how about a plus 8x? All right. Good. How many times does x squared go into negative 5x squared? Negative 5 times. And we repeat one more time. Let's just bring it on down to make sure. Negative 5 times this whole divisor right here should get negative 5x squared, get a minus 5x, and get a plus 30. And you know what? We can do a subtraction if we want, but hey, didn't we already kind of get our mx plus b taken care of right up here? The rest is superfluous at this time because we don't need it. I don't need the remainder. I can ignore it. I don't even care what happens right here. I've got this. I did it correctly, so there's your y equals mx plus b. And so as a result, I think we've got an oblique boundary at y equals x minus 5. Now, I don't know if I'll be able to find the best window for this. I might see a little bit. I'm going to have to kind of move this over to see what that function is. I'll try. Haven't looked at this function in too much detail before, so I'm not sure if the window will suffice, but I am willing to give it a try just to see if we can find that vertical boundary at a couple vertical boundaries, and then we're going to get that crazy oblique in there. So give me a sec. I'm trying to do two things at once here. There we go. And I'll divide that by the denominator, which is lengthy as well, x squared plus the x and minus the 6. All right, so let's see. I'm going to stay on that right there. Let's just see if this is worthy. And if it's not, maybe I'll change it up or give up all hope. Not bad. Could have been better, could have been worse. Notice we do have a couple of vertical asymptotes. It looks like one at x equals -3, one at x equals 2 coming from the denominator. And then, we've got this going up right here and this coming down right here. Let's see if it is what I was thinking. So I'm just going to go to my y2, type in x and then -5, hit graph. And again, is it ideal? Nah, if I honed in on it a little more, I'm sure we'd see it better. But you can take my word for it or do a little investigation yourself there. And it looks like from both sides, you could really tell right here, that graph is going to get closer and closer to that diagonal line. With the end behavior, it's not going to touch or cross it. All right, pretty cool. That worked out nicely. I'm going to bring this back over just for future reference. And let's go ahead and just answer part C. So, I hope you've been kind of looking at this and thinking about this question. Can a rational function simultaneously have a horizontal asymptote and an oblique asymptote? No. One or the other. Again, we looked at that yesterday. Horizontal, depending on the degree. If there's no horizontal, which would be the conclusion right here, if it's one bigger on top than on bottom, you get the oblique. All right. Good. Let's go hit the next slide. So a very, very quick warm-up here, and I don't mean to dumb this down too much by any means, but I think it'll help us answer these questions right here. So if I ask you 0 divided by 4, you get an output, you get an answer of 0. If I ask you to do 4 divided by 0, of course that is an operation we can't do, and that would be undefined. All right, keep that in mind as we go through this process. And what we want to do is just solidify some of the characteristics here, a couple asymptotes. And again, the oblique is in there as well, but I won't emphasize that too much with these problems. And then the intercepts, y and x. So a couple old ones, a couple new ones, and then we'll do a few examples to round this out. So first and foremost, vertical asymptote from yesterday's lesson. We just kind of talked about this as really it's the zeros of the denominator. That's basically what we said. Now, there is a sort of a catch or an exception to the rule here where we would not get a zero. We would not get a vertical asymptote with a particular zero of the denominator, and we will see that come up on the next notes worksheet. But for right now, let's use it. So whatever would produce 0 in the denominator makes the function undefined. That's this case right over here, everybody. That's kind of why I did this part. So whatever makes the denominator 0 makes the function undefined, and then we get our vertical asymptote. All righty. Horizontal asymptote. This is what I'll do. Those were the 3 scenarios from yesterday. Very simply compare the degree of the numerator to the degree of the denominator. So remember, just depending on the degree of the top being smaller, the same, or bigger than the degree on the denominator. So let's just write that piece in there, and we'll get some practice on that in just a moment. Y-intercept, talk about y-intercept of a variety of functions, of course, and just in the most basic description, I'd say it's the value of y when the input, when x is 0. That's all. Now, here's the one I really like. What about those x-intercepts? We've talked about x-intercepts on a variety of functions, and very simply, it's the value or values of x when y is 0. Of course, just know in the coordinate plane, it hits that x-intercept when the y value is 0. So what does that mean, though, in a rational function? So that's what's kind of interesting about this piece. And I'm just going to put up an example very, very quickly so you can think about it, but then I want to elaborate in a little more detail here. So I will erase this momentarily, but what if I gave you something like this? If I gave you a rational function that looked just like that, and I said find the x-intercepts, and all you know about x-intercepts is it's the value or values of x when y is 0. So think about this for a sec. So your instinct would probably allow you to do that. You would say the y value is 0. And then what would you do from there? What would you know had to be the case in a fraction in order to make the output or the answer 0? And again, there's a reason I did that warm-up up above. How do I make the answer in a fraction 0? By making the numerator 0. Does everyone see that here? To make the answer 0, the numerator has to be 0. Because 0 divided by anything, other than 0, 0 divided by anything would give us 0. And that's it. So really, the way we're going to phrase it, guys, is the x-intercepts come from the zeros of the numerator. Because whatever makes the numerator 0 makes the entire fraction 0. All right, good conclusion right there. I like that. Let's get rid of this piece. And let's just go do a couple examples. So we'll come up with the characteristics. If we can use the characteristics and maybe sketch just based on what we've learned over the last couple days, great. You know, if we can't, we'll pick up the graphing calculator and let that do its work. So you're not point plotting. I don't expect that. That's not what I'm after here. Just understanding the algebra that goes behind these, the characteristics themselves, and then obviously potentially utilizing them. So 2 asymptotes, 2 intercepts. I would love for you to, pause and see if you can do some of this stuff on your own. But obviously, you can stick around for the explanation however you'd like. Doesn't matter. All right. So I'm going to do asymptotes first. And so in this case, vertical asymptote comes from the denominator. What would make the denominator 0 here? A value of 1. And so as a result, vertical asymptote at x equals 1. And let's kind of do this piecemeal over here too. Let's just kind of get a coordinate plane going and throw some tick marks in. Again, if it works, great. If it doesn't, we're not going to lose any sleep over it. We'll let the graphing calculator do the work for us. So x equals 1, vertical asymptote. Perfect. Let's do horizontal asymptote. So, horizontal asymptote, everyone. Compare the degree of the numerator to the degree of the denominator. They're the same. So we just go out to the ratio of the leading coefficients, 2 on top, 1 on the bottom. So in this case, I'm hoping you would see horizontal asymptote, y equals 2. And we come right over here, of course, and let's just get that in place. Perfect. Y-intercept, probably have to do a little calculation on this. We have to just make x 0. So this would be the y-intercept. And we get 2 times 0 on top, which is 0. 0 minus 1 on the bottom. And so as a result, it looks like when 0 goes in, 0 comes out. So it looks like this graph is going right smack through the origin. There we go. Looks good. Last but not least, x-intercepts here. And keep it nice and simple, right? How do we get a y value of 0? The top has to be 0. So all I have to do is 2 times x, so the numerator, set it to 0. Divide by 2, and we still get 0. And I think we already knew that was going to be the case, as it did go through the origin. So in this case, we've got 0, 0. When that y was 0, it's 0 that produces it. All right, so unfortunately that didn't add too much to the discussion here, but oh well. Let's see what we can do with this. So we should get a fairly basic hyperbola here with a couple boundaries. And obviously if I look at this graphically, there's going to be one part of the hyperbola to the left of this boundary and one part of the hyperbola somewhere over here to the right of this boundary. And the fact that it has to go through this point right here, really to me, there's only one way we can draw this. It's got to go through this point, and it's got to obviously come closer and closer to this vertical line right here. And the end behavior, I'm assuming as we go to the left, is going to hit that, go closer and closer to 2. So long story short here, let's see if we can kind of draw this out, something like this, give or take. All right, perfect. There, I think, is the part of the hyperbola to the left of our vertical boundary. There's definitely a part to the right, And I guess I would ask you, think about this. Do you think it's going to be up here, or do you think it's going to be down here? I think we have enough information to make a good conclusion from this. Well, I came up with this from two different perspectives. I knew that there was not another x-intercept, right? We would have found it. There's not another x-intercept. So can the boundary, or I should say, can the curve kind of go like this as it meets the two boundaries? No, because it would have to hit an x-intercept. And so I think it's going to be that one. Also, guys, I am not entirely sure if you remember this from the previous day's lesson. What's the multiplicity on that vertical asymptote? Do you remember the odd versus even investigation we did yesterday? And if this goes down to negative infinity on the left side of the asymptote, this has to go the other direction to positive infinity. And so I kind of knew that had to go up there. If this was an even multiplicity, that would have changed it. They would have gone from both the same direction. All right, well, regardless, I think we sketched it pretty well there. I'm going to just bring it up as maybe a verification of that. So let's see. Do that right there, get rid of that stuff, and I'll be relatively fast on this end. And we've got this, x minus 1. Not a great window. Let's go back and zoom standard. There we go. And did I do it justice? Yeah, hopefully it was decent. Great. Let's go get letter B. Again, I would love for you to just kind of pause the video and do some stuff on your own. Play around with it a little and just see if you're getting them right. There's no sense just listening to the same explanations because it's the same math. But if you need it, of course, utilize it. All right, so I looked for the vertical asymptotes first. Let's go to the denominator there. I'm seeing x plus 5 and x minus 1 in the denominator. And so as a result, I'm getting x equals negative 5 and x equals positive 1 as two vertical asymptotes. Cool. Let's go get this vertical, both of them, on the coordinate plane here. Give me some tick marks if you get a chance. All right, so what did we say? 1 at negative 5. 1, 2, 3, 4, 5. There it is. Great. 1 at positive 1. There's another one. Cool. Horizontal asymptote. Degrees, guys, of course. Degree of the numerator. Smaller than the degree of the denominator, so you know right away it's going to y equals 0 in the end. So let's go ahead and throw this piece on. Again, as it goes to the end, that would be the case. All right, y-intercept. Let's see if we can put some things together with this. Y-intercept, I'll come down right here, and I know the top, again, just putting in 0 for x. Again, 0 for x. It's pretty easy when it's in this nice standard form right here. It would look something like that. You get 3 on top, of course, and you get negative 5 on the bottom, so it looks like negative 3/5. An ideal one? No, but it is what it is. So negative 3/5, right in there, give or take. And last order of business here is to find any x-intercepts. So remember, take the numerator and set it to 0. And so I do exactly that, and of course, I get negative 3, and so I should see one at negative 3 and 0. Interesting. So I've got 1, 2, 3, and 1 right there. So there's really not much to work with, is there? And again, if there's not, it doesn't matter too much. We will, of course, go ahead and pick up the graphing calculator. I might take just a guess and see what happens here. So there are 3 parts, one to the left of this vertical boundary, in between this vertical boundary, and to the right of the vertical boundary. The only information I have to some degree is that I have a couple points within the 2 vertical boundaries right here. I have that one and that one. And it's tough to tell. It looks like obviously this might do something like this. I don't know if it comes back down or comes back up. Most of them kind of shoot the other direction. So I don't know. This is just speculation, to be honest. But I would say something like this, give or take, maybe would be the case. And I like doing that investigation on the multiplicities of the vertical asymptotes. Remember, guys, these are both odd multiplicities. So as I look at this -5 right here, on the right, it's shooting to positive infinity. So on the left, it has to shoot down to negative infinity. I think that has to be the case there. And then here's your horizontal boundary at y equals 0. And same deal here. As you look at this vertical asymptote, on the left side, it's going down to negative infinity. Because of the odd multiplicity on that asymptote, I know it sounds crazy, but I'm pretty confident in that. The only issue I would have is this piece right here, whether it went up or down. But I don't know. I think that's at least a legitimate guess. You know, we could do a little T-chart and get some more ideas there, but I'm not interested in that. I'm just interested in seeing if the math and the deductions that I can create from that are legitimate. Anyway, let's go ahead and see how I did. Maybe you did this as well, took a good educated guess on it. And yeah, it's tough to tell. It's not a great window there, but that would be the case. So here's the left part. Here is the middle. I was right on that. That was the fortunate thing. And then here's the right part. So mine looks actually better than the graphing calculator just based on that window. Looking good. It's a winner. All right. Let's go do the 4 characteristics one more time. So here we go. Vertical, horizontal, y-intercept, x-intercepts. Again, maybe you're doing this on your own at this stage and just checking. Totally your call. Again, just really interesting graphs that emerge from rational functions there. And we're just really exploring their characteristics and kind of seeing, again, cause and effect. From here, what emerges? Okay. Well, I'm getting x plus 4, or x plus 4 squared on that denominator. Interesting. So here, if you look at the vertical asymptote in the denominator, it's an even. Keep that in mind. But we do have one at x equals -4. I'm pretty sure that'll be the case. All right, nice. Horizontal. Degrees, everybody. X squared on top, x squared down on the bottom. Go out in front, 2 over 1. All right, so y equals 2. Also looking pretty good to me. Y-intercept, you're just going to put 0 in for x. And I'm actually hoping at this stage you're starting to see when you put 0 in for x, when it's in this nice standard form, this stuff just all goes to 0. And you're just left with really what's on the back end there. So I'm getting 0 and then -24 over 16, which happens to be -3/2 or -1.5. So I'm seeing that. And then last but not least, let's set that numerator to 0 and see what happens. Huh, this is an interesting one. It seems right away, everybody, that I can take out a 2 there, or really divide by 2, because it's an equation. I'm going to do it that way. That 2 kind of is just in the way at this point. So I'm going to divide everything by 2 and clean that up a little bit. And then factor, of course. Now you guys are experts at factoring. I know if I let you to your own devices, you could pull this off. And it looks like you're going to get -6 and 2. That looks pretty good. So here's -6 right here. Here's +2 right here. I'm interested to see if we can make this happen. So here's your vertical boundary, guys. Let us graph it and bring this to some closure. So to the left, I have a couple boundaries right in here, and it goes through this point. Got this horizontal boundary and vertical boundary. And I mean, I'm seeing it has to kind of be that right there. Now, again, if you kind of look at this, in terms of to the right of this vertical boundary, has to go through those 2 points in a very particular way. Maybe it's kind of shooting up here. Now, also, if you remember, look at the degree on the asymptote. It's an even multiplicity. So to the left of the vertical asymptote, this shoots down to negative infinity. Because it's an even degree, it also shoots to negative infinity from the right. And so as a result, it should look something like that. Now, it's tough to tell with these because the more complex they are, the more weird things happen. I don't know if this actually if this graph crosses the horizontal asymptote first and then comes down, or if it just kind of goes up there. I'm going to take a quick peek and see. It's tough for me to tell. I would have to plot points in order to see it. But, wow, that's a pretty lousy looking graph. But I think for the most part I'm on target. But I am curious about that one piece. So I'm going to just take a moment. I have it. So if you're not interested, don't sweat it. You can probably end the video at this stage. But I'm interested in seeing what happens just to the right there. Did it actually cross that horizontal asymptote first and then come back down? You know, again, just the more complicated the equation, the more things could potentially happen. All right, let's see. So I was right on at least my drawing. That did look pretty good. I'm going to just trace this out. Again, more curious than anything else. Does it cross the 2 at some point? Doesn't look like it, but I'm wondering. Yeah, this is a little too slow. Let me hit the table. So actually, it doesn't look like it does. So I think I had my drawing correct. I was just curious if that was going to be the case. I mean, it could for all I know there, but I'm going to go with it and kind of leave it at that. But you see, drawing as poorly as I drew it, at least it was meant. It works. Hey, I'll wrap it up right there. So kind of the graphical characteristics and some good stuff, and obviously look at those oblique asymptotes when you get a chance. Thanks.